So once again, thank you all for coming. For those who don't know me, my name is Sean Lozano. I am a sophomore here at Mount SAC, physics student, and also heavily involved with the Astronomical Society here on campus. If you're interested in astronomy, it's a wonderful resource. I would like to invite everyone to come to our meetings next semester, seeing as how we are currently ending this current one. It's awesome to see some familiar faces. Hi, and some new people as well. So I just wanted to give y'all a little bit of a background of basically what this is. I recently spent the spring semester at JPL doing the CERI program, which is an internship meant for undergrads at community college to get some research experience under their belt. We work with a mentor in a variety of different fields, whether that be computer science, engineering. I don't have any experience in that, but I do have experience with astronomy, so they put me in a project doing some planetary science, and this is all really new to me. I learned a lot. I'm excited to share it all with you. It was also a lot to ingest, seeing it was kind of basically starting from like ground zero. So with that being said, I'm going to be referring to my notes heavily. I apologize. And I'm also going to try to speed through this, seeing as how it was originally a 45-minute presentation given to scientists within the planetary science division. I recognize that unless, like, show of hands, anyone here a scientist in the planetary science division at JPL? Okay, then I'm going to try to explain things, and if y'all have questions, feel free to raise your hand. I'll do my best to explain it to you. I'm still learning as well, so without further ado, we'll go ahead and get started. Thank you. So the title of our presentation is Using Craters to Probe the Regolith in and Around Oriental Basin. The first thing that we ask ourselves when we're considering lunar regolith is, what the heck is lunar regolith? It's a really good word. I didn't know at first, but to make it simple, when we look at the moon, what we're actually seeing is a surface completely covered in what scientists call regolith. Regolith is one of the most important features in understanding the moon's history, and to put it more plainly, lunar regolith is more common, we can commonly refer to it as lunar soil. Lunar regolith is essentially the loose, fragmented material that covers the moon's bedrock surface. Grain sizes can range from fine particles up to rock fragments, which I'm hoping y'all can see, like in this picture here, which is taken from the Apollo 11 landing site. We've got some astronauts' footprints here, and these would be like, I guess, like larger rocks, which would be considered part of the lunar regolith as well. We can gain insight into how the moon's original surface composition evolved over the past billion years by understanding how regolith develops. The structural characteristics as well, and what it can tell us about the lunar subsurface. They're all tied together. So, lunar regolith develops as impacts strike the lunar surface. When meteorites strike the lunar surface, they shatter rocks and redistribute material across wide areas. This process has been ongoing since the moon's formation, and every impact event contributes to the development process, further breaking down larger rocks into smaller fragments. The ancient highlands surface, some of the oldest terrain on the moon, has been exposed to over 4 billion years of bombardment. The highlands regolith layer has been measured to be approximately 10 to 20 meters thick by seismic experiments at the Highlands Apollo landing sites, which we have a great picture right here of what that looked like. So our research was actually looking at a region known as the Oriental Basin. I would like everybody just to take a second to, like, in their mind's eye, like, visualize the moon. And I want to tell you that the Oriental Basin is not in your mind's eye. It's not there. It's actually going to be on the western side. It's not visible from Earth. But if you'd like to know what it looks like, it's actually this region right here. It's actually the youngest impact basin on the moon, and it formed around 3.8 billion years ago when a 40-mile impactor basically just crashed right into the moon. It's known for its 3 concentric rings, with the largest ring being 3 times the width of Massachusetts. I know that might be hard to kind of visualize, but I think if I remember correctly, it's like, if you can imagine the width of Montana. That is what we're looking at here in the largest of the 3 rings. So like I said, when the rings formed, when a 40-mile impactor crashed into the moon, it blasted 816,000 cubic miles of ejecta into the atmosphere. That is roughly 135 times the combined volume of the Great Lakes here in North America.
May I ask what you mean by the width of Massachusetts?
Like if you were just to go horizontally along the state of Massachusetts, you take the width of it.
Where to where?
From the sea to the western border. It's roughly. Yeah, it's roughly. I understand that you have a coastline and it meanders. Yeah, so excuse me, sorry. Also the tidal wave, when this 40-mile impactor crashed into the moon, it sent up material about 11 times higher than Mount Everest. And this tidal wave of material basically formed what you see as the 3 rings that are there. None of the actual rings are the impact crater itself. Yes?
I wonder if you could show us the rings in the picture.
Sure, yeah. Is it hard to see? I'm so sorry. I'm going to see if I could. So this would be the outermost ring here. I'm trying to be more precise. So this would be the outermost ring here. This would be another inner ring right here. And the final ring would be just inside of that. And what you do have in the middle is another mare, which is basically just remnants of volcanic activity at the very center. So when I'm mentioning the highlands region, the highland region is actually going to be basically just everything kind of outside of Oriental Basin itself. It's hard to tell from this picture, but actually as you start to go deeper into the rings, you're actually losing elevation. So hence highlands as you start to go further and further out away from the basin center. So the material after the, like I said, none of the rings themselves are the impact crater. That was probably obliterated when the material that was kicked up started sloshing around. And finally the inner ring would have formed from the collapse of like a central peak that was too massive to remain stable. And that is more or less how you get to Oriental. From this map here, we've created, actually this is a colorization of an existing map. We've located 29 geological units in Oriental Basin and in the surrounding highlands. Different geologic units might have different subsurface rock content. And some of the notable geologic units include the Montez Rook Formation, which creates the double rings that you see here towards the center. There's another ring here, and then there's one in there. That's the Montez Rook Formation. There's the outer rook and the inner rook. There's also the Hevelius Formation, which is pretty much the main ejecta blanket. When we use the term ejecta, what I'm describing is all of the material that gets kicked out of the crater. That's going to be a term that I'm going to be using quite often throughout the rest of the presentation. And then finally we have the Mondra Formation, which is composed of impact melts. So impact melt is basically just cooled, now solidified rock that was previously liquefied in the impact and over time starts to cool into something very, very dense. So the Mondra Formation is composed of that impact melt. So going into this, we do have a little bit of expectation created by prior research that informs our project. We expect to see fewer rocky craters beyond the basin rings in the typical highlands, especially in areas that have been previously identified as having low radar return. The term annulus just refers to a ring. So a crater's ring that has low radar return basically means that when they inspect this area with radar, they're not getting any rocks to send any signal back. So they think, okay, low radar return, there's probably nothing there. Also, we expect to find fewer rocky craters around areas with low thermal inertia. Are there any physics people here that can explain, that might be able to answer what thermal inertia might be? So no pressure, no pressure at all. It's something I had to learn myself. So basically, thermal inertia is just a solid's ability to be resistant to the change in heat. I like to think of, like, if you go out to the desert, and you're going up to a rock, like, it's not going, like a really huge boulder, it's not gonna get incredibly hot very fast because the sun's been hitting it. But over that time, it's going to hold onto that heat, and long after the sun goes down, you'll still feel the heat radiating off of it. Basically, just meaning that the item or the object itself is just resistant to temperature change, causing it to release or gain any heat transfer. And then we expect to find rockier craters in the Oriental Basin, specifically around the Montes Rook Formation, which is identified as having high thermal inertia. So we're thinking if there's high thermal inertia, there's probably rocks. If there's low thermal inertia, there's probably no rocks there. If there, as papers have suggested, areas that have enhanced radar return are probably also going to be rocky areas. So once again, low radar return, probably no rocks. High radar return, probably some rocks there. So this is more or less what we should be expecting as we're going through our project.
Is that an assumption you can make because of the low atmosphere of the moon?
I'm not sure how much of that has to do with the atmosphere, because I do believe they have actually done studies where they were looking at the moon with radar from here on Earth. But I'll go into how we are able to gather this data and make these readings in just a few slides. Good question, though. So impact craters serve as natural probes into the lunar subsurface, making them invaluable tools for regolith studies. There are several reasons why craters are particularly useful for this purpose. First, impact craters are ubiquitous around the lunar surface. No matter which region you're studying, we can find craters in various sizes and ages that we can analyze. Second, and perhaps more importantly, crater samples beneath the surface, craters sample beneath the surface and excavate buried materials. So the depth of excavation is directly related to the crater's diameter, basically meaning larger craters are probably going to be excavating deeper into the lunar surface. This provides us with a way to sample materials from different depths without actually drilling into the moon. Large enough impacts can penetrate the regolith layer and excavate bedrock material by displacing it into that ring of ejecta, which is known as the ejecta blanket that surrounds the crater. And by studying these ejecta deposits, particularly the presence of rocks, we can gain insights into the depth of the regolith at different locations, as well as what lies beneath. There are also some challenges that go into this as well. The rocks excavated by impacts have a finite lifetime in their on the surface. That's because we don't really think about it, but there's still things that are pummeling the moon now these days. So we've only really been looking at the moon for a very, very, very short time, considering how long it's actually been there. As things are constantly bombarding things, it can create a little bit of uncertainty about how long the crater has actually been there that we're looking at. Also, rock-free craters are not necessarily indicators of a thin rock-free regolith, as a crater could be older than the lifetime of the rocks. But never worry about how long a crater's been there, because we actually have a way to work around this, where we are looking at a certain type of crater, which are called cold spot craters. To address this issue of variation in rock count due to a crater age, it's useful to consider craters confined to a known age range. That would be our cold spot craters. These young craters are surrounded by a region of regolith, commonly described as fluffy, and that would be what creates the cold spot that gives it its name. The signature fades within about 1 million years, so this is kind of like anomalous for certain types of craters. I'm going to kind of go through this here. One indicator that you're actually looking at a cold spot crater would be the rays that start to extend from the center. And I think this would be called the albedo that goes around it. The rays are the albedo, which is just basically like very reflective rock surface that is exposed to light. So that's what gives it that look to it. Like I said, these cold spot craters, the rays, it will have fluffier lunar soil around it, which allows us to kind of see that it's there. And these cold spot craters are really young; they're under 1 million years old. So to answer your question, like how are we able to find these craters? How are we able to use radar and all these different types of technology to make our observations? Well, we use the LRO Diviner craft right here, and this was actually launched in 2009. So a lot of the data that we're getting back is actually really new, relatively new in comparison to how long we've actually been going to the moon. And all of the data that has been aggregated by the Diviner probe has been aggregated into a website that's actually open to the public. I invite everyone to check it out. It's super cool. It's really not that hard to play with. And it would be, it's LRO Quick Maps. So this is basically what it looks like. It's going to give you a surface of the moon. You can zoom in really close, and you can actually make out details on craters that are going to be like under 100 meters in diameter. So when I'm going to be mentioning Quick Map a lot during this presentation, and I just want to give you guys a visual idea of like what it is that I'm talking about. That's going to be this website, this tool right here. So the crater's cold spot can be seen by overlaying maps, which utilize one of two methods. So this would be like what you're looking at when we are using the Quick Map tool. Yellow here would be a cold spot crater that we are observing. So let's skip through here. Cool. So the first overlay that we would use is an H parameter map, which utilizes the density of the regolith layer that is surrounding the cold spot crater that we're looking at. That would be this map here. I guess the darker areas would be actually fluffier regolith, and the lighter areas would be less fluffy, less dense. Also, we have the ability to see cold spots with a temperature anomaly map, which look like this, where we're looking for those deep blue squares to say like, okay, it might not necessarily be exactly on the crater that we think we're looking at, but as long as you're looking in an area that has a darker blue overlay or a darker red overlay, that's usually a very strong indicator that you've identified your cold spot crater, and especially too if you are able to see that it has those rays sticking out of it. So there are also, we're talking about craters, but not every crater is going to look identical. There are 4 crater morphologies that we investigated throughout our study of Oriental Basin. The morphologies include bowl-shaped craters, which you'll notice here are very smooth, no real irregularities. This might be like what you picture in your mind when you're thinking of what a crater might look like. These are really fun because basically the names are exactly what you think they are. We have flat bottom craters, which the bottom of these types of craters are basically flattened. They lack structure, and while the walls are steep, they're also not as smooth as the bowl-shaped craters. They're a little bit more imperfect. We also have concentric craters, which appear to have an inner ring, which you can see right here, or rim. We also have our central mound craters as well, where there's a clear mound in the center of the crater. Some important factors that cause craters to exhibit a certain morphology are the velocity of an impactor, the thickness of the regolith layer as well, and the density of the substrate, or like the underlying rock layer underneath the lunar soil. Studies have determined that concentric craters form when, that's these right here, that they form when there's a large enough difference in strength between surface layers and when the top layer doesn't collapse enough to fill in the hole. When you do have a collapsing of the sides of the walls of the crater, that's usually when you're gonna get the flat bottom. That's what kind of gives it that, that's what fills everything up on the bottom of the crater itself. So that's enough of the background that you would need to know to kind of get the gist of what it is that we're looking at, the types of craters, how they form, what lunar soil is. Now we're going to start to move into the methodology of our study and kind of talk about how we performed our investigation to find out the density of the lunar regolith. So this right here is a slide on data distribution. Let's see if there's, yeah, it does. Okay. So in comparison to the rest of the moon, here is Oriental Basin, and each of these dots is going to be a crater that we were setting out to investigate. This data set was provided by a study by Williams in 2018, and that study provided us with diameters in meters for potential cold spot craters, as well as their geological coordinates. So the data set then was divided into three ways. There were three team members on this project, and they were divided into longitudinal strips with about 75 craters per intern. I myself believe I might have had this side of the strip, which is really cool because I got to kind of check out a lot of craters that were not only in Oriental Basin but outside as well. Whereas I did have a colleague that was, I can show you on this one, it's much better. I did have a colleague that was like mainly on this side, and she wasn't seeing quite as much various terrain as I was. So once you actually go further than 50 degrees from the equator, the craters are 50 degrees from the equator. The craters are too hard to see due to the lighting geometry near the poles. Since the sun is always low on the horizon during the day in those regions, it creates long shadows that makes it hard to basically make out any rocks that would be around the crater. So that's why you can kind of see there's like some dead spots that we weren't really looking at up on the poles up there. So we're also going to just take a quick look at more data distribution. Each one of the rings is basically just how far, like one crater radii away from the center, and kind of get an idea of how far some of the craters were from Oriental Basin proper. We'll go into this a little bit later, but for now, we're going to keep moving past it. We also have data distribution over the geologic units, which we were investigating as well. But most importantly, how we performed this, our research was broken down into three phases. The first phase, like I mentioned earlier, was to go out, use Williams' data set, and go find some craters using quick maps. I explained a little bit of how we were able to find those cold spot craters earlier, so we're going to keep going. So once we actually identified our cold spot craters, what Quick Maps actually is like a mosaic of images that are all sort of stitched together. These are all called knacks. So we would go and we would find our crater. We would find a knack that actually properly showed us the right lighting of the crater itself by the moon. We want to be able to kind of see rocks around it. So that was done by considering the incidence angle, which is just basically the position of the sun, where if the sun is directly overhead, that would be 0 degrees, and if it was like just setting exactly on the horizon, that would be 90. So here's some good examples of some really hard to see incidence angles. As you can see, like there's shadows along the crater rim. So if our goal was to count rocks, it would be really hard to really count everything, considering you can't really make out what's in the section. Alternatively, when you have a really low incidence angle, you end up starting to wash out a lot of the boulders themselves due to like the boulders matching the albedo color that's in the rays of the cold spot crater. So a lot of this is something that you had to consider when you're going through this whole process.
So what's the optimal angle here? Is it like 45?
We found it's like roughly around 60 degrees.
60.
Yeah, around 60 degrees is where you're able to create long enough shadows that the rocks start to really stick out, but not so much that the shadows start to overtake any other of the surrounding rocks that were there in the image. Yeah, we also wanted to make sure the resolution was under 1.5 pixels per meter. That'll come into play a little bit later. Once again, we also were considering crater morphology. This was a little bit hard because we had like some very basic ideas of what a crater should look like or how to classify them. But a lot of this we were just kind of like, okay, go find the crater. What do you think it is? So like with this just being your basic 4, like there might be variations that might fall somewhere between like a bowl or a flat bottom, and it really is up to you to use your best judgment to say like, what do you think it is? They did give you a lot of freedom in that to make your own determinations, which was really cool, but also a lot of pressure. So that probably made that portion of the project pretty hard. So once we actually go through, we identify all of our cold spot craters, we move into processing, which if anybody here is a fan of astrophotography, this is actually kind of fun because yeah, it's a very similar process. Like you actually have to apply calibration frames to actually get the proper stretch to really be able to make out a lot of the rocks in the image. It's done like they're actually downsampling the images. I had mentioned that we were looking at images that were under 1.5 meters per pixel, but we actually had to process these images so that they were exactly at 1.5 meters per pixel when we're looking at them. And why we do that is because this is actually an ongoing project. This spring, I'm actually part of a chain of interns that have been going for about like 2 years. And in order to eliminate any bias by having us have access to images that have higher resolution than what was available, they basically just kind of like turned up the pixelation on the image so that it made everything just a little bit harder for us, but I guess more fair. Like I said, we're eliminating some bias here, so it did make some sense. Aside from calibrations, we also applied some georeferencing, and we also assigned projections as well. The projections are pretty important because basically what we'd use was what's called a sinusoidal projection, which was centered at the crater to project the data. And this was done so that we can preserve the shapes of the rocks and the craters regardless of the crater's location on the moon. For instance, if we kept the same projection centered on one place on the moon, those craters which are further from the center of the projection would look really warped, and that would mess up our count. It would be hard to use. And so what this does, before, you might kind of notice that like this crater here on the left before we processed it looks a little bit more imperfect. It might be on a slope, it might be on some like uneven terrain, but when we actually process it through ISIS, it really flattens everything out. This is actually going to help because we're measuring the area of the crater itself to basically find the center and properly record where these cold spot craters are located on the moon for later. This is starting to get into a little bit more of the nitty-gritty of it, but when we are actually doing our second phase of the project, or I guess now this is now our second phase of the project, where we're actually going into and starting to conduct our boulder count. We had to basically make constraints as to what was the area in which we were going to be counting. If you go too far away from the crater, if you're in an area where there's large crater density, it's really tough to know, like, am I counting rocks that came out of this crater, or are these rocks from a neighboring crater? So in order to eliminate any of that guesswork, what we did was we just basically measured the crater, determined its diameter, and said, okay, we're gonna make another count area that's basically one crater radius further out. So this inner ring, that's the crater itself. This would make the outer bounds of our crater count area, and everything that's in here and outside of the green lines, that's fair play. That's what we're looking at. That's what we're going to be counting.
Sean,
Yes.
did you intentionally then, because there are some craters on the moon that are overlapping, did you intentionally keep those out of your survey?
Absolutely. We actually found a lot of different crazy craters. We found some that were on slopes. We found some that weren't even there. We went to inspect it. We're like, wait a second, there's nothing here. So that was pretty cool. And so there was a lot of I don't want to say guess and check. It was just kind of like playing hide and seek and seeing what we get and determining whether or not the crater was actually viable to be included into our total count. So there's like a lot of preliminary work that went into just getting to the point where we can just count rocks, which I guess on a side note was kind of surprising for me because I really thought this was going to be like, all right, let's just go in this project, we're going to count some rocks. How hard could it be? Turns out it was pretty. It's pretty interesting, yeah. So now as we're counting our rocks, what we're using a different shapefile here. So where we were using circles that we were drawing ourselves to determine the boundaries of the crater, we're now using polygons to go in and determine, okay, like that's definitely a boulder. And there is some criteria for the boulders that we're actually looking to count and which that we're looking to exclude. So here I have, it's hard to see, don't worry, I'm gonna make it bigger right now. Those are two boulders that I counted. And as when you start from a very zoomed out version of what you're looking at and you want to get in there and say, okay, is this a good boulder? Should I count this one? As you start to zoom in, this is a really good example of what you're dealing with. Everything becomes incredibly pixelated. And there's a lot of subjectivity as like going through and determining like what's a boulder, what's not. And so y'all might ask, like, how did we make those determinations? What did we include? Well, what we were looking for are boulders that are a minimum of 3 meters. So that's why the downsampling became incredibly important, because we now had incredibly precise way of measuring and saying, okay, we want something that's 2 pixels. If 1 pixel is 1.5 meters, if we take something that's a minimum of 2 bright pixels, we can say for sure that we can include this boulder in our count. So we use what's called the bright pixel rule. I mentioned that's 2 touching bright white pixels. So I'm not sure if it's easy for you all to see, but this would be a determining factor to say, like, okay, these 2 pixels here, that's bare minimum of what we can include. If we are looking at something that's going to be a little bit bigger, those rules start to become a little bit less strict. Like as you can see, there's maybe 4 pixels here that I counted. None of them are incredibly bright, but you have to start using a bit of contextual clues. Like, are there shadows that you can clearly see that would be going in the opposite direction of the crater's bowl shadow? That's usually a good indicator that you're looking at a rock as opposed to like an actual, another smaller crater. So as we're going through our crater count, we would pick out a maximum of 6 boulders for every crater that we're looking at. Once we counted 6, we're saying, okay, we're moving on. We're moving to the next one. Here's where I'm going to stop. I'm going to take a quick pause to take any questions. I had mentioned I'm really not sure how I'm doing on time yet. Okay, so I think this is actually a really good place to stop. We can turn this into like kind of like a serial thing if y'all are really interested in finding out more about the results, what we found. If not, then I would probably say like this could be a good place to ask questions, or even if you gotta get going. I'm gonna go with you first. I'll come back to you.
So on that last slide, you said that you stopped counting at 6 boulders.
Yeah.
Why is that?
Because honestly, that was, I don't want to say it was arbitrary, but I think that we had just determined like this is enough. In previous iterations of the project, they had basically counted like every boulder that they could see, every boulder that was big enough, and that took forever. It was hard for them to move past one single crater, especially if it was like a particularly rocky crater. And I have seen some larger craters where there could have easily been hundreds. So we said 6. 6 was a good place to stop. I'm sure there's probably a stronger reason for it that I was not privy to, or I maybe just, if I asked, I had forgotten at this point. But yeah, for the sake of speeding everything up and getting through it and kind of having results to show from it. Oh, I'm sorry, I'm going to go to you now, Professor Halverson, if you have some questions about the question.
For the Oriental Basin that you were observing, it was on the dark side of the moon?
I wouldn't say the dark side of the moon. It's just not forward facing. So what if you'll notice, like the sun did hit it at certain and there was times when the sun was able to travel across the sky and lengthen the shadows or shorten the shadows at certain times of day. Yeah.
Okay.
Yeah. Oh, Professor Halverson.
Yeah, I was gonna say, there's a big map of the moon over there.
Yeah. So it would be definitely on this like lower side here. I'm not sure from this view if you can actually see it. I don't believe so. I don't think that from this view you can actually see it. It could be. It could be. Yeah, I would also recommend y'all go to the diviner. It's on the back. Wait, can you see the back side of the moon? Never mind. Sorry, that went over my head. Anyways, or maybe the poster.
The poster's showing the side that faces the Earth, but you had mentioned in the beginning of the presentation that this was on the far side.
Yeah, it's not the far side. It's more on the western side. So like it's like around the corner here. It's not exactly like behind what we would see from our position on Earth. Yeah. Sorry if that was unclear. Yes.
Sorry if I missed it, but why were you counting rocks, or what was the purpose of counting the rocks?
Yeah. So what we assume is that a rockier crater probably would be deeper, and also it would probably mean that you had less regolith on top of it to actually be able to penetrate through to the deeper part of, or penetrate through to the bedrock. If there was more regolith, then it probably wouldn't be able to reach that deep. And so as the impactor actually created that crater, if there was less regolith on top, it would probably kick out more rocks. So by counting those rocks, you can kind of use different mathematical equations that have been set out in previous papers to say like, we can really tell you exactly just how thick the regolith is in this area. Yeah. Yes.
How many craters would you say you mapped out?
I personally did about like 73. I think we had about like some people had just under. I think some people had exactly 75. So maybe like 223 maybe altogether for our project between 3 different interns. Yes.
You mentioned the ejecta blanket. How is that formed and what exactly is it covering? Is it over the regolith, underneath the regolith? How does that work?
Yeah, so the ejecta blanket is basically everything that's kicked out of the crater center when a meteorite actually impacts the moon. So it's if you can kind of think of it this way, it's like everything that's now the ejecta blanket has been ejected from the crater. Yeah, and it's a mix. You'll have regolith. You'll also have rocks as well. Yeah, good question. Yes.
Also, what is a regolith?
So regolith is the lunar soil. It's a really fancy way of saying lunar soil.
Okay.
Yeah, yeah. I'm glad that you asked that just to kind of make it clear again, because people are like, what is he talking about? Thank you so much. No, thank you. Okay, I'm gonna pause here. I'm gonna pause on question. Okay, one last one.
Did you use the temperature maps to find cold spot craters?
Yeah. So if we went back a couple of slides, there was the red colored overlay, and then there was like the blue colored overlay that we were using in quick maps. The blue colored overlay would be the temperature anomalies that we were looking at due to the fluffiness of the lunar soil just basically not holding on to as much heat as maybe like a rock would as the sun went down and it was observed at nighttime. Okay, I'm gonna continue on. We're getting now into a little bit more, there's gonna be a lot of charts coming up, so hold on everybody. I hope y'all are into charts. I was actually, really quick thing, I was really gonna be like, here's some more slides, and then just put like a couple pictures of like playground slides, but I really didn't want everyone to come at me with like pitchforks and like torches, so I like really held back. Thank you guys for sticking around though. I'm really excited. Okay, so moving on, let's look at our, let's look at some results here. This is basically our cold spot craters as they were measured. This is kind of like all over, this is an overlay of the moon that we were given. This one wasn't my graph. It's really pretty, so I kept it. But it's really hard to tell because they forgot to include a legend with it to tell you like what type of, like what exactly these colored spots mean. I believe what this is larger spots are going to be larger craters, and then the numbers here are going to be different crater morphologies. So we're just, without further ado, we're going to skip through the next few slides. This is basically just telling you how we were able to create these graphs. We were using some data binning there. Here's another overlay from the distance from Oriental Basin itself. And now we're going to go into something that's a little bit easier to talk about. These are just more of our, I'm going to tell you now, these are all preliminary results. We basically were able to aggregate all of our counts, and all of our measurements in a matter of like a few days, and also go and create these. So these are going to be like really early results that we haven't really been able to parse through too deeply. So just want to add that into everything. So don't want to say take it with a grain of salt, but we still haven't had a chance to like fully deeply analyze what our results mean. So basically how to read this chart is you have here your crater diameter, and this is going to be the percentage of craters that contain a certain amount of blocks, where if it's yellow, you're going to have no blocks, red is going to be 1 to 3 blocks or boulders, and blue is going to be 3 or more boulders. And as you can see here, inside each of these bars, you're going to have the number of craters that had the amount of boulders that we counted as we were moving through. So this is all the crater diameter for each of the craters that we investigated within Oriental Basin, where if you were going back and thinking about the map with all the circles, this would be like the innermost of those circles. This is basically everything that we have counted, so for all of the circles. Interestingly enough, I want to just remind everybody that we expected to find more craters, craters with more rocks closer to the center of Oriental Basin. And as we move further away from Oriental Basin, we expected to find no rocks. That isn't what we're seeing here on these charts. If you'll notice, more or less, at a certain size in crater diameter, it's really all more or less evenly, not evenly, like similarly distributed, which was kind of interesting. That went against what we were thinking we were going to find. I'm going to go through another data set. This is going to kind of go through each one. Give you guys a second. I'm not sure if everyone's trying to digest that really quick. But more or less, that's what I was saying. As we started to move further away from Oriental Basin, we didn't necessarily experience a large change in the amount of rocks that we were finding around each of the craters. Yes?
So this is telling us something about the thickness of the regolith.
Yes.
Right?
Yeah.
So you were expecting that the regolith further away from the from the Orientale impact point, that it would be deeper.
Yes.
And so if it was deeper, you'd find fewer rocks.
Fewer rocks, exactly.
But you didn't find that, so does that mean that it wasn't getting deeper?
The jury is still out. That's actually the really interesting thing about our findings. We'll go a little bit further into this as we go into our discussion slides in a little bit.
Right.
I just want to go over a few more slides. These were actually this was actually some of the stuff that I was tasked to map out for everybody. So for these charts, I was actually, instead of doing the variability in the amount of rocks due to crater size, variability in the amount of rocks as we move further away from Oriental Basin and crater size, I was actually doing the types of craters that we examined as we moved further away. And these are, I want to go back and remind everybody, all of these things are all tied together. The types of craters that that are formed, the amount of lunar regolith that is in these areas, and the amount of rocks that you would count are all tied together. So here's another interesting factoid is that we didn't really also find a lot of difference in the amount of craters. In the type of craters that we looked at as we move further away from Oriental Basin. If we look here, let me double check this. I might have flipped these around a little bit. I'm gonna keep moving. We would probably expect to see different crater types as we move away, but mostly what we found are flat bottom and bowl shaped. I might have actually flipped out my talking points from the last slides. Most important thing that we determined from those last slides is that we didn't find any difference in the rocks. Just really quickly, I'm going to go through these. This is just the crater types that we found as we move further away from Oriental Basin. This is kind of an interesting point. There is another slide on this. I'm just going to go through these really quick. I probably should have skipped through these a little bit further. I'm sorry. I apologize. Let's go into a little bit of discussion about basically what all these results mean. I think that would probably help clarify some of the points I was trying to make. Basically, our overarching result is that there was no clear variability in block count or crater morphology observed as a function of distance from Oriental Basin, which goes against what we were actually expecting to find. There were definitely rocks in all of the craters, larger than about 200 meters throughout the entire region. And what we would probably do different in the future is, instead of looking at the difference in the amount of rocks that we count as we move further away from Oriental Basin, we would actually look at it as a function of the geological map. So instead of saying okay, how far are we getting away from the center? Let's see what the difference in the amount of rocks that we find. We're going to say, well, let's look for things only in areas that have impact melts. Let's look for things only in a certain area of Oriental Basin. Or let's only compare this now to something that's specifically only in a certain type of geological unit in the highlands. If we kind of switch things around, we're hoping to find some different results that would kind of prove what we were trying to test. Also, counting all the blocks at each cold spot crater in the future, it might actually make it help to prove some of the things that we're trying to set out to find. That what we found, or what we actually did find, wasn't really working with the amount of blocks that we were setting out to count so far. So this is another slide. It's not the same thing. As I mentioned before, this is actually an ongoing project. So the previous iterations of the project, instead of looking at the lunar highlands, they were focused specifically in the Mare, which was an area that is like east of Oriental Basin and the highlands that we were looking at. An interesting note about the flat bottom craters that we did actually find in the highlands is that their abundance, we observed, could indicate that the impacts there were actually low energy, which supports a hypothesis that was presented in the Williams paper where we gained our data set. We also observed a lot of flat bottom craters at a range of diameters, which could indicate that the population of impacts that formed these particular cold spot craters were low energy and interacted with a target that had weak regolith over a stronger material like rock. So once again, by observing a lot of flat bottom craters in the area that we did find, we're thinking that these were actually formed by something with like a weaker substrate, a weaker bottom layer, but it does indicate that, a weaker top layer of regolith, but also indicate that it had something stronger underneath it. That's how these form. So we're thinking, okay, if we know how these types of craters form, we can kind of start to guesstimate just how thick the regolith layer was in the region where we observed these flat bottom craters. Also, the fact that we see them at many different sizes suggests that the regolith thickness varies a lot across the region throughout the project where we were investigating. We see bowl craters as well, which tells us that one, the impact that formed those cold spots was a higher energy, or two, the regolith is much deeper at these locations. So you were kind of asking, like, how does this all tie together? Like the amount of rocks that we were able to see, or what difference does it make what shape the cold spot crater was that we were looking at? This all starts to tie together where we're actually able to draw some idea of how deep the regolith layer was in these areas. So let's take a look. This is what I was mentioning. We did see a lot of bowl shape and also flat bottom craters where in comparison, when observing the Mare, they actually found more concentric crater types, which was actually really surprising for us. Just to kind of continue on this, flat bottom craters are thought to form under very specific conditions, and we can estimate that the thickness of the regolith at all of our we can estimate the thickness of our regolith at all flat bottom craters. This is something that we had to kind of confer with our mentor over, because this kind of was, we were out, pardon the pun, but we were sort of out of our depth with this, and also our mentors were a little bit like, that's kind of funny. Our mentor, Dr. Catherine Elder, calculated that the regolith thickness based on a relationship identified through impact modeling by Pruer found that on average the regolith is about 36 to 46 meters thick in flat bottom crater locations. Flat bottom craters are sensitive to a high contrast in strength, usually between like a soft regolith target over a soft regolith target over something more dense underneath it, a more dense substrate. So that's why we can measure regolith thickness at these craters. The derived value is thicker than typically assumed based on Apollo measurements, but there is some indication that the Apollo landing sites might not be representative of all of the highlands. There's always some uncertainty in using scaling relationships derived from modeling because they might not have been able to accurately represent the strengths of the material in their modeling. So what we're basically saying is we think we have an idea that we could say that roughly the regolith layer at these types of craters is about 26 to 36 meters deep, but we're not really sure because we're using models that can at times be inaccurate. We can't necessarily say with certainty that this is how deep the regolith layer is at these crater types. So what this graph is basically showing is this is actually how from the flat bottom craters, concentric craters, and normal craters are created in the scenario that we're observing, where we're actually seeing low impact velocity with a high strength difference, which as the crater grows in diameter will tell you the type of crater that you'll actually get from those from those combinations. And it is possible that there is some error built into this, into our research. So a possible source of error is that some craters were on a slope, as I mentioned earlier. That makes rock counting a little bit different, a little bit difficult. It's thought that possibly some of the rocks that were exhumed from these craters possibly just rolled away. We can't really say for sure, or that there might have been rocks there, but they're no longer there because of the terrain that they're on. Also, some of the knacks that we were using had shadows that washed out ejecta. That also kind of affected our rock count a little bit. This one's probably my favorite. It's another source of error is that there's a level of subjectivity that goes around the decisions of like what is and is not a rock. This actually probably was like the hardest part of the entire project. So basically, what I'm showing here, 2 different craters, roughly around the same size. On the left, you actually do see that there are a lot of smaller rocks around the terrain. You can probably mostly make it out here. This is one of the rocks that we're looking at, and we're like, this is like a corner case of the bright pixel rule that we're trying to use. Like we can kind of see, and it's really hard to tell from this projector, that there is something there, but we're not really sure. Similarly, on this side, there aren't as many small rocks around it. But certainly we do see that there is something there. And as we zoom in, you'll see that the boulders are actually really, really close in their shape and their size. So we're thinking like, what do we count? And how do we keep a level of consistency as we go through these counts, not only on our own terms, but as we start to deal with other people's counts in the project as well. Just to let you know, like we didn't choose this one because I was thinking in my head I'm thinking there's a lot of small rocks. I'm gonna guess that this is actually gonna be just another small rock with maybe a little bit of the ejecta blanket kind of blending in. I'm not gonna count it. Whereas this one definitely had at least one bright pixel, and really it was the only thing that was in this area. It really stood out. So I said, okay, you know what? We're just gonna count it. We'll include it into our count. You'll say, well, what if everybody's actually doing this? Like, you know, if everybody has this level of subjectivity, how do you know that your results are actually not incredibly skewed? Well, because we actually split up our observations by longitude, we didn't actually observe any variation between all of our counts. We were all pretty consistent. So with that being said, I think it's pretty safe to say that that this source of error from subjectivity probably didn't skew our result as much as it might have. So I went ding, then we checked it off. Now we've basically come to the conclusion. Just to kind of go over everything that we've talked about so far, I just wanted to remind everybody that first, we did not observe variability in regolith thickness as a function of distance from Oriental, inferred from either rockiness or crater morphology. Additionally, there does not seem to be a clear difference in blockiness between craters of different morphologies. As we compare our study of the Oriental Basin highlands to previous studies of the Mare, we see a lack of concentric craters in the highlands compared to the Mare, which is consistent with a thicker regolith in the highlands. Furthermore, there isn't an obvious difference between the diameter at which craters become rocky. However, we do see an interesting difference in crater morphology between the Mare and the highlands. The abundance of flat bottom craters in comparison to the Mare that had been studied by previous intern projects indicate that regolith thickness could be highly variable across our study area. Ultimately, these preliminary results require more analysis, and additional studies on craters in the highlands would improve our statistics. Basically, when we all kind of put our heads together, we were discussing the results, we all kind of determined that, you know, there haven't been a lot of counts in the exact area that we were looking. In fact, we believe that we might have been the first. So it's really hard to kind of compare our count to another and say like, okay, this is more or less on track with what's been established, which is kind of cool, this level of uncertainty, because I guess you'll have to pardon the pun, our research could be considered groundbreaking.
Mm-hmm.
So before the pitchforks and the torches come out, I'm just gonna say thank you all so much for coming. I'd like to give a huge thank you to Dr. Halverson, who is my sponsor on this project. And he met with me on Fridays, took a lot of time out of his own personal time to come in and help out with this project for me for this class. I'd also like to, he's not here, but I'd also like to thank Dr. Burita, Professor Burita, for presenting the Siri project. Thank you to Astro Club, thank you to everyone who showed up today. And also thank you to JPL for hosting this. I hope they hear me from all the way over in Buckingham of Leverage. Thank you so much. Okay, I guess this is another time for questions. I could probably take a few, if anybody still has any. I know that the last section was a little bit rough, so if I could help clarify anything, I'd be glad to help you with that. Yes?
I was just wondering what the significance is of knowing the regolith depth of the moon and the mare, as you call it.
Yeah, so regolith is pretty funny. It's everywhere. And as we start to look at what humanity's future could look like on the moon, I think understanding the depth of regolith in areas that we would like to land, in areas that we may consider like habitable, yeah. We need to know a lot of this. And we were thinking like maybe we can actually use lunar soil in 3D printing. We can mine it. It could be a hazard as sharp lunar soil, sharp lunar regolith can actually be a hazard to spacesuits that are out there. People can sink in it if it's too fluffy. On top of that, if you want to look at it from like a purely like planetary science perspective, like looking at lunar soil is actually a great opportunity to understand like the geological history of the moon. Like we can kind of guess like what the underlying rock in that crater that we're looking at is composed of, given how thick we think the lunar soil is on top of that crater that was formed. If it was particularly dense or not dense, and a lot of that just goes into understanding the geological history in the same way that we would actually do it here on Earth. Yeah.
Awesome, thank you.
Any other questions? I'm glad everybody got it. There's not a lot of questions. Because I don't know if I got it at first. It took me a while to wrap my head around. And I'm always available. I'll be here if anybody does come up with something and they're like, could you go over that one more time? I'll be glad to. This was long. Thank you for sticking around through all of it. I know it's a lot. Thank you so much.
Thank you, Sean. Thank you.